So I'm gonna hope that this works. I've never tried it before. I'm trying some screen share web recorder thing. So hopefully that this works and you can see it. But I apologize if you hear any dog barking. But my presentation is gonna be on derivations and differentials. So first, we're going to go and kind of define what a derivation is. So the definition of it is if S is a ring and M is an S module, then a map of abelian groups. D from mapping S to M is a derivation if it satisfies Leibniz's rule. So Leibniz's rule is d of f of g is equal to f differentiation of g plus g the differentiation of f for f and g in S. And Leibniz's rule can also kind of be thought of as the product rule from calculus. So if all of us most likely remember, but I'm just going to rewrite it here for you. It is the differentiation, apologies for my handwriting, of f of g equals f of dx of g plus d dx f of g. Okay. And then just like a little quick reminder of abelian groups, has 4 properties: associativity, closure, inverse, and identity. Okay. So let's see what else we have here. Oopsies. All right. Before that, if a little more about this is if S is an R algebra, then we can say that D is R linear, which is just saying if it's a map of R modules. So the set, it looks like this: DER of our reals is kind of what we're using here. Mapping S to M is an R linear derivation, and R linear comes up a little bit more later on. R linear derivation is the set of R linear derivations from S to M, which is also naturally an S module by multiplication, and the multiplication is defined by BD F mapping, or an element of F to B of D of F in M. Okay, just a little bit on that. Let's do the next one. Okay, so we're going to do an example of a derivation. So take S in the ring of polynomials, x, y, and z in the reals. Given the polynomial p, x, y, z to be x to the 4th y plus xz cubed minus x y squared z plus yz, we want to know what is its derivations. Okay, so given this polynomial, p of x, y, and z equal to that polynomial, we want to know what are the possible values of derivations on p. So for this, we want to recognize that what we're doing is the derivation of r from s to s. Okay, so what we have to do is, let me see how I can make this smaller. Oops. Okay, I'm not very tech savvy, so I don't know how to make this smaller. Okay. Okay, maybe I can do that. Just moving things. That doesn't move it. Okay, whatever. Okay, so what we're gonna do is essentially we're just kind of taking the partial derivative with respect to x of the polynomial ring, and then the partial differentiation of each individual x, y, and z. So what we're gonna do here is, let's first do the derivation of x, or with respect to x of p. So we're going to get 4x cubed y plus c cubed minus y squared z. Again, just taking partial derivatives, just pertaining to x for this polynomial. So now the next one we're going to do is with respect to y. And again, we're going to get x to the fourth minus 2xyz plus z squared. Plus z, which is again partial derivative with respect to y, and now partial derivative with respect to z is going to be 3xc squared minus xyz plus y. Okay. So this derivation is a polynomial linear map, S to S. So we're, like I said earlier, we're just mapping two polynomials to each other. So this is spanned. So the derivation of this is spanned by partial derivative with respect to x, y, and z. Oops, z. Okay. And then just a reminder, span, smallest linear combination in a subspace. Okay, cool. So now we're gonna go to, differentials. So what differentials are? So for the definition, it's saying if S is an R algebra, then the module of Color differentials of S over R, written omega S over R, is the S module generated by the set that we have here, D of F, such that F is in S. And it has to have these following properties. Has to follow Leibniz's rule and R linearity. And like I said, it's just saying for all A prime in R and B prime in S. That's just saying for all of those things. The map of the derivation of S to omega S over R is defined by D mapping F to D of F elements in there. And this is an R linear derivation. So next, what we're going to do is, again, just saying that the derivations from S to M is just a set of derivations taking polynomials and returning elements of M, essentially. So let's kind of look at an example of how to apply this. Let's do it on this side here where I have some more space. Oops, no. Okay, so an example of differentials is we're going to take R. There we go. R to be the field of real numbers. And then R adjoint X to be the polynomial ring. In X over R. Okay, so the formal derivative, formal, not formula. Formal derivative is the map D mapping the polynomial ring to itself, the polynomial ring. And this is an example of an R derivation. So the module of Color differentials is just the polynomial ring itself, R of X. Okay. That's just a simple example of differentials. Now, let's see. Our universal property map. So, the universal property map follows from the map D, mapping S to omega S over R. So, given any S module M and a R linear derivation, given any S module M and R linear derivation, we're going to just call it E, mapping S to M. There's a unique linear homomorphism, E prime, which maps omega S over R to M, such that E equals E prime of D, which again, this is since going from S to M is the same as going from S to omega prime S over R to M, we're going to say E prime is defined by the formula E prime of df equals E of f. And we get this by plugging in f, so E times f equals E prime of D times f, which gives us E prime df. Okay. And then this formula kind of defines a homomorphism because the relations among the df are that also satisfied by ef. Okay. That's kind of a little bit on the universal property map. There's more to it, but before I kind of go over a little more, I wanted to go over through some definitions. Just to kind of remind everyone of some things. So, okay, I lied. We're going to first do or state proposition 16.1, and then we'll come back to the universal property map in the proof of this proposition. So proposition 16.1 says if S is equal to the polynomial ring in R variables, then omega S over R is equal to the direct sum from 1 to R of S of D x sub I, the free module on the D xi. So just kind of reminding us of what a free module means again, just that if we let A to be a ring, then a free module is a direct sum from I in I of M sub I, where M sub I is isomorphic to A for all I. Okay. So now, before we get onto the full-on proof, is here I'm going to do a couple definitions just to kind of remind everybody of some things. So first, we're going to do epimorphism. So an epimorphism is an onto or surjective homomorphism. Homomorphism. Okay. So that's a quick definition of that one. And then morphism, again, not too crazy here, is just a map between two objects. Okay. So next one is, oops. We're going to do direct sum. Again, nothing too crazy here. We did a little bit of it just now, kind of with the free module. But direct sum is if we let an I from I in I be an A module, then the direct sum let's see, start down here. From again I in I of M sub I is equal to the summation of I in I of X sub I for all xi in M sub I, where all but finitely many x sub i's equals 0. Okay. And then functors are something we've worked with this semester already. So we're all pretty familiar with it. I'm just going to kind of give a brief definition of it, even though it's kind of hard to kind of define functors as is. But just something brief is a functor, let's say F, is mapping category C to category D, which consists of some data that satisfies certain properties. So the data that we're looking for are objects, which kind of states an object f of x in D for every object x in C, and a morphism f of x to f of y with the map f of f in D for every map, not map, every morphism x to y in C. So those are the datas, and then some properties that it has to satisfy is just um, that f respects composition and and then f sends identities to identities. Okay, cool. So now it's where we're getting to kind of the fun stuff, is actually proving that proposition, which we will do in 1 second. Okay, so first we're gonna go with first defining this universal property map over here, which is going to send S to, I'm gonna do my best to draw these out on here, S over R, which then goes to S, and then there, all right, so we have this property map, and this implies that there exists maps dx, dy, and dz, or del x, del y, and del z, such that the partial differentiation with respect to x of, so the partial differentiation with respect to x of x, y, z is if we take, let's say, x, y, z in this polynomial ring, and then we're going to do the differentiation or the partial differentiation with respect to x, of, let's say, this polynomial ring to S over here, then what we're going to do is we're going to take the partial derivative of each individual, let's put variable. So partial derivative with to x dx dx equals 1. The partial derivative with respect to x of dy equal to the partial derivative dx of dz, which is just equal to 0. And this is, again, just coming from taking the derivative of x with respect to x is, for the first one, derivative of x is going to be 1. Can't take derivative y, can't take derivative z. Those are all going to be just zeros. And then, again, just following through, doing the same thing. Partial dy of dx, can't do it, so you're going to get 0. Dy of dy, is going to be 1. And then dy of dz, again, 0. So if we do this all the way throughout, we're going to get that this implies, if we add them up, dx plus dy plus dz is the map from omega s over r to S3. Okay. So more generally, we can kind of say the partial derivative of, let me give myself a little more space here. Okay. We can say that the derivative x with respect to x sub I is an R linear derivation from S to S, which induces an S module map, and that is going to be del sub I from omega S over R to, I mean, not S, omega, yeah, S over R to S. And this is going to be carrying our dx sub I terms to 1, and then all other x sub j terms to 0, which is kind of what we see above there previously. So doing this, if we put the first partials together, we'll get an S module map, which will be del sub I from 1 to R, mapping omega S over K to SR, which is going to be an inverse map. Okay. So next we can say, if we have a map R to S of rings to the S module, omega S over R, and the derivation, let's write this out a little bit more so you can kind of see it. All right, yeah, so if we have a map R to S, again being rings to an S module, omega S over R, and then the derivation is going to be D from S to omega S over R. This being a functor, we can get this mapping R. Okay. Omega S over R, or oops, that's not what I want. Omega S over R to S. Okay. And to show that this is kind of a little bit of a functor, we can look at the commutative diagram. So this will kind of look like this. So it'll be a commutative diagram of rings, which we can think of kind of as a morphism of pairs of phi mapping R to S to R prime S prime, which results in an induced morphism, which is going to look like this. Have S with the derivation over here to omega S prime R prime. S prime, and then again, same derivation map that we have there. Okay, so looking at this kind of mapping that we have here, we can see that the bottom horizontal map is the morphism of our algebras, and then the top the top horizontal map is a morphism of S modules. So the module omega S prime over R prime is an S module because of the bottom map. And then we can see that the S linear map omega S prime over R to omega S prime over R prime is obtained from the universal property of omega S over R. And this is applied to the R linear derivation. Let's write this out a little bit. Okay. This is applied to the R linear derivation. Let's write that. Derivation. S to omega S prime over R. Which is the composition of the map S to S prime, with the universal universal R prime linear derivation S prime to omega S prime over R prime. Okay. So you'll see typically in applications that the map R to R prime is the identity and phi as a homomorphism from S to S prime. You can also see that the S linear map, let's move it a little bit here. Oops. Oh my goodness. Sorry, I'm so not tech savvy. Okay. There we go. Yeah, so you can also see that the S linear map, oops, S linear map, omega S over R to omega S prime over R prime. This we can interchange with the S prime linear map. And we will get S to the negative 1, or S to the 1, S to the 1, functor S omega S over R, mapping to omega S prime over R prime, which is its equivalent counterpart. And that's kind of all that I have to prove Proposition 16.1. We got through everything, because if we go back and look at, go back. The proposition over here, just saying about omega S over R is equal to the direct sum. We had proven that a little bit earlier on here. Oops. Oh my goodness. Let's see if I can find it. Oops. Let's see if I can move this right. Let's see over here. You can see it. Right here we have the direct sum of del sub I from 1 to R of omega S over K to SR. Well, that's kind of all that I have. I hope I did an okay job explaining this. I apologize if it was a little bit hard and kind of all over the place. I'm really not the best with using computers. This is the kind of first time I'm using this tablet. But here are my references that I used. And if you have any questions, you can always send me a email and I can try and answer it as best that I can. All right. Bye.